Okay.
First, what's your name?
Yeah, so hey, I'm Ian Miller. I am coming from the psychology department. I ostensibly am studying social psychology. It tends to be this more sort of social complexity thing. I do a lot of social network analysis, and I study memes. So today...
sorry, just normally like we just go around.
Of course, yes, yeah, let's do that.
Yeah.
My name is Kurt Geyer. I'm doing cognitive neuroscience.
Luke, PhD in nutritional science.
Nick, PhD in the study of evolution and book history, and I'm working on a database of old letters. Ahmed, I'm on my before my master's in microbiology.
Cool. Well, welcome everyone. Any other procedural?
That's it.
Like, cool. Come on in. Yeah. Yeah. So, why would a psychology student ever need to use databases? Well, I have so many answers to that question. But before getting into any of that, I thought, and I hope you'll bear with me, that we could get actually back to before databases, get to the time of data, actually perhaps even the time before data, perhaps even the origins of the universe itself. Maybe let's not get carried away. But what I'm going to try to do here, start off with a presentation and then we've got some exercises. But what is data? And what's a database? Because that's going to be closely related to what data is, we'll say. And then some examples. Right in the browser, there will be a JSON MapReduce example, some stuff with SQLite, some R and SQL stuff, some Python, and then we'll wrap it up. So I don't want to actually stop here and wait for everyone to install the software, but I'm curious to just quickly hear who all was able to install any of the stuff. Do you guys have SQLite installed? If the answer is no, it's not a problem. Because everything is, you can follow along with the notebooks online, so you don't actually have to run this stuff. You can run it later. But how about, just out of curiosity, Jupyter and IR kernel for R? Anyone have Jupyter for Python? Okay. For R, anyone? Okay, so maybe some of you will be able to run the Python examples. So we do have some of that stuff. So, okay, why don't we jump right in and orient our epistemology here. So data itself, the word is plural, just so you all know. Datum is one data, I guess. Came from Latin, and it's kind of weird. It means gift at a certain level. But we use it now to mean a measurement or a fact that we get from direct observation. And I found the word data used historically to mean gift here because his gifts do not match his word. Quia non substitunt dictus data. So it's kind of weird how gift became the way that we use it now, but think about that. Data is kind of a gift. So anyway, looking at the world, there's this whole empirical approach based on observations, measurements, values, yada, yada. Everybody's doing something different here. So whatever your data are going to be, whatever your observations are, will be very specific to your domain of inquiry. So I'm starting from like the first principles here. Data is just whatever it is that's in your domain that you're studying. It can be recorded or it can be encoded. It could be marks on paper. It could be arranged as numbers in tables. Digital encoding is something that we're actually going to dwell on for a little bit. I'm going to say that data are quite frequently the basis for scientific inquiry. So that's a statement about empiricism, but it's true for at least a lot of science. So let's talk briefly about table topology, because this is something that happens long before we get to Excel and common separated values. A table is really just a way of organizing data. Mostly what we're talking about here is it's a two-dimensional matrix. There's rows, there's columns, there's metadata potentially, rows and label column names. And the table can be situated in a couple of different ways. Now, I'm just calling them wide and long because that's a bit of a convention. But what we have displayed on the screen here is a wide table where the different columns are different variables, basically. And then the different rows are different observations. So this picture is states in the United States, and the columns are different grains and stuff like that. So each cell is the intersection of a row and a column, and it corresponds to the observation of that variable for that state. There's a kind of newer way of orienting tables called a pivot table. It's a way of doing marginal calculations or summations inside a table. It's common with things like Excel or massive data sets like you get from the census. And that's basically useless for what I'm going to be talking about. So really it's just, so wide tables, or I should mention long tables. So a long table is where you've really only got 3 columns. You've got an ID, every observation has a unique ID, and then a variable and a value. Every single row consists of a single observation. And so if you're going to record the value for wheat in New York State, then your variable name is going to have to say, New York.wheat, and then the value will just correspond to whatever's exactly inside the cell. So these are 2 different ways to organize your data. But again, we haven't even gotten to the database yet. All right, we're going to blast through this. But information is a property of the universe. I think this is a statement that's a little bit controversial, but more and more, I think this is going to be true. So information itself is kind of related to entropy at a certain level. So the information that you have about something is kind of the certainty that you have. The principle of entropy is kind of not knowing something. And the guys who figured this out, so the line of reasoning here starts with Maxwell's demon, where he figured that there was this kind of low energy way of sorting the particles into a room, and wouldn't it be cool if you put all the hot energy on one, or the hot air on one side of the room and all the cold air on the other side of the room, and you would have effectively reduced the entropy dramatically in this process. And it seemed like a paradox until people like Shannon figured out that there was actually a deeper relationship between entropy and our knowledge about the universe. And the reason I mention all of this is that 1 bit of data is equivalent to 1 kind of iota of certainty, let's say. There's a relationship here, or a correspondence, between the basis of the binary number system and the amount of information that that single digit can contain. So from there, we have a bit, we have a 0 and a 1. And we scaffold up to talk about bytes, so it's just a collection of bits. And once we have bytes, we have enough information to actually start doing some interesting data encoding stuff. And this is where we start getting into the craziness of comma-separated values, line feeds, quotation marks, yada, yada. I'm going to point out 1 character in particular. So this is ASCII. It is the first common encoding. Every CSV file you get, or every CSV file you got for many, many years was an ASCII encoded CSV file. And this specific number here, 7, is, it's actually supposed to be 9. It's the horizontal tab. So tab delimited files are a way of using ASCII to encode structured information. And the more modern way of doing it is UTF-8. That only came about in the 1990s. We won't dwell on encoding very long. But data are whatever your research is. And then encoding the data as information is something that maybe, depending on your type of research, you have really expensive hardware that encodes your information. And then you store it in something like a computer. So let's talk about databases now. It's a kind of information system. It's software fundamentally. You download it, it runs. Sometimes it's in other things. So there is a database inside Firefox and Chrome. We're going to mess with that. There's a few types of databases I'm going to describe extremely briefly. So we've got flat files. That includes tab delimited files and CSVs. This is actually the level that a lot of research is at. Basically the 1960s. We were talking about ASCII. And I mean, it's relatively primitive. Relational databases is what actually a bulk of this presentation will be about. 1970s era technology. Most researchers have not caught up to that level. We've got the 1980s, which were a terrible era of incompatible file formats, and a lot of people are stuck using Excel and SPSS. And they effectively have databases. It's a desktop-sized database, but people don't necessarily think about it as a database, but I would like you all to consider it to be a database. Finally, when we start to get into our own millennium at least, key value storage, this is pretty interesting. Graph databases, which I'll discuss briefly, but that's for networks, and then document databases. So flat files, basically it's just a table. It's like a table if you were to literally print it on a sheet of paper. So there was a whole lot of typewriter metaphors going around back in the 1960s. And a table, if you printed it out, you would actually literally print a tab character, and it would cause the print head to move over a little bit, and you would get your columns all lined up on the printout. And that's literally why tab limited files use tabs to separate the fields. Again, we're kind of primitive 1960s era technology here. I will point out that Excel can load and save CSV files, but it has its own dialect. Of course it does, just because that's kind of the way that Microsoft does this. But the point is that you can have a CSV file that is not compatible with Excel, or a CSV file that is difficult to load in Python for whatever reason. So I'm going to point out that the Excel dialect is specifically, a quote is the 2 tick marks. It's not a single tick mark quote. That'll screw you up. Double quotes are the way that you put actually a quotation mark inside a CSV field. And then at the end of each line is a line feed and a carriage return. So anyway, okay. Binary blob data objects are like an Excel file, and this is what you see if you open an Excel file. You can't use it unless you have a program like Excel that will decode it for you. I discourage the use of this style of database. A key value store, I'm not really going to describe this very much, except to say that HTML5 local storage is a type of database that's actually running in everybody's web browser right now. And you could actually begin messing with the database as we speak. Also, Bigtable is it's one of Google's many database offerings, and it has some pretty interesting characteristics. So I think it's worth mentioning, but we're not going to actually describe it. But a key value storage is typically used for the kind of research where you need some kind of buffer. It's really maybe for very high throughput research. So I don't actually have much of a use for this. But relational databases are really what we're going to talk about a lot here. I will be describing SQLite 3 a lot. It is a very basic database. You can download it in one file. It's a single exe file on Windows. It comes pre-installed on OS X. It's very easy to install on Linux. And it gets the job done for a lot of people. It's not as powerful as some of the other database engines, but you can get started immediately. And so we're going to do a little bit of that at the very end. For heavier lifting, I would recommend Postgres. That's what I use. It's open source, it's free. A competitor to it is MySQL, and Microsoft, of course, has their own style. The basic idea of a relational database is that you have a bunch of tables, and these tables are related to each other somehow. So this picture depicts a couple of entities. So this is a store. This is a model of a business domain. So these are sales. This is the date of the sale. This is the store that the sale occurred at. And this is the product. And you're frequently going to see the use of IDs, row IDs, as a way of linking one table to another table. So a sale is what occurs when you have when you sell a product at a store at a certain date. So the sales object links out to each of these different things. It has relationships to each of these different tables. And when you sort of resolve all of these links, then you actually get the complete picture of one purchase. But the actual data is not complete, it's spread across a whole bunch of different places. So a relational database is actually a really powerful metaphor for scaling up certain types of highly regular data. When you've got great certainty about the columns that you're going to be using in the type of work that you're going to be doing, because you pretty much lock these column names in stone. If you have that much certainty, then relational databases might actually be the thing for you. One of the things that's so nice about them being fixed in stone is that it's very hard to violate some of the constraints. So you can actually have better research if you ensure at the database level that you can never have a null value or a missing value for a certain field. That's something that you can accidentally do with Excel or with SPSS, or even with R, actually, unless you program your own assertions. And part of the reason why relational databases are as prolific as they are is because when you're dealing with money, it ends up costing money to lose data. It's a little bit different from academia, maybe, but these are very well developed in the industry, and it's partly because they need to be reliable. And so I say it's a very good match for certain types of research. So document-oriented databases do not have the same kind of fixed schema. The column names, well, they don't exist, and they can be constantly shifting. These are some very modern databases, so CouchDB, MongoDB, and in particular Hadoop, which has gotten an awful lot of traction in certain big data fields, like life sciences. These types of databases operate on a different type of data structure that's much more like a tree than a matrix, like rows and columns. So what I have here is, this is JSON. Not really going to dig into what the significance of any of these things is, but I mean, this is a picture that corresponds to this text representation here. And you can see that there's kind of a sense of nesting, that there's a probability of true and false, there's a prediction that is false, and there's a number that's probably somebody's ID or something. And you can kind of intuit the way that this data structure contains nested information. I say it's a tree because some of these boxes appear indented and inside other boxes. And that's something that's topographically extremely difficult to do with a tree, or sorry, with a table like an Excel file. If you want to nest things inside Excel or R, it gets really hairy. So sometimes if you switch to a different database system, you can take advantage of different types of data structures that might actually match your problem domain. So I use document-style databases for Twitter. I collect stuff from APIs, and I do not always know the type of data that I'm going to be getting. So I like to just take everything and throw it into a database. I don't have guarantees about the types of data that are going to be present when I go out scraping. So I can't use a database that requires a fixed schema. I need something much more flexible than that. And so a document database is pretty useful for that. It's also the case that JSON is a pretty widespread data format online. So that can be pretty handy because a lot of APIs will just give you JSON directly. So you throw that in MongoDB or something like that, and you can start doing interesting stuff pretty quickly. Finally, I'm going to mention graph databases, which are useful for representing networks. And a network is nodes and edges. So this is a 3-node network. 2 of these nodes are people. This node actually represents group membership. And this can, again, it doesn't really map onto rows and columns very easily. So it doesn't, you can't really represent that kind of relationship as a table. Or at least it's not that easy to. And there are certain types of queries that are hard to think about in terms of rows and columns because they're very interdependent queries. So you might say of this database, for example, tell me all of the people that are connected to this, this group node called chess. And this is Bob, and that's Alice. And you can think about that question easily enough and say it in English, but it might be pretty hard to actually represent that question as SQL. So just kind of think about that in the back of your mind, because we are going to look at a lot of SQL. We're not going to look at any graph databases. But the basic idea is there are certain things you can think about. You can easily come up with certain questions, but it's sometimes hard to use your query language to write the question, to map out your desires in terms of the query language. So, okay, so databases, there's a bunch of different ones, and the right one for you has entirely to do with the problem domain, the type of the work that you're doing. So what I have here is a really quick demonstration with MapReduce. If you people want to follow along, you can actually. I should have mentioned earlier, but the presentation is online. Let's see, it's Ian Dennis Miller. It's going to be Databases SQL. So, so okay, if you want to, it's iandennismiller.github.io/databases-SQL. I'm gonna basically just do this, and so you can also just watch. But all right, before we get into SQL, I wanted to show a style of querying the document type database. This is a technique called MapReduce, map and reduce, whatever. And it's the main paradigm for querying these really big kind of document-oriented databases like Hadoop. Map and reduce are it's like a two-part algorithm. There are two functions, and if you can figure out a way to represent your question in terms of these two patterns, or these two kind of paradigms, then there are certain advantages to the kind of computations that you can do. So I really briefly walk through a numerical example here, and I'm going to go through this line by line. Let's say that we have a map function. So what this is it's a function that takes a function. And let's say that our function is just square whatever you give. And we'll give it the values 1, 2, and 3. So we're going to square each of those, 1, 4, and 9. And that's the essence of mapping. Mapping means you get a vector of values, and you take a different function, in this case, x to the second power, and you apply that one function to each value in the vector. So that's mapping a function onto a vector. And it gives us a vector as a result. Now, reduce takes a bunch of values and summarizes them into a single value, somehow. In the example that I'm going to do here, we'll just create the sum of everything. So what our reduce function will do is it will take a function, and that function takes each map value, and it's just going to add it to whatever the previous sum is. And so our map values are 1, 4, and 9. And this is the way we break down the computation. 1 plus 0, so our running total is 1, our running total becomes 5, our running total becomes 14, and that's the end of our vector. So we have reduced the vector 1, 4, and 9 with a function that just sums them, and we have a value 14. Okay, that's an extremely, I mean, it's so basic that you can hardly see why anyone would want to do that. But like I say, when you're talking with large-scale data, it becomes more useful. So we can start to get a feeling for that by going into an example here. Well, I guess I did have the URL. So, so what we're going to do is go into the developer tools, and I'm going to do a couple of things here. So I'm actually just going to copy and paste. But all right. So the way to get into the developer tools is view, in Chrome at least. If you're using something else, then I leave it to you to figure out what you're doing. So, okay. Now I'm in the developer tools. I embedded some JavaScript in the presentation itself. So this live demo ought to work, right? Famous last words. So, okay. Actually, I'm going to take this out of full screen because I think that's going to be problematic. I'm going to take both of these out of full screen, so give me a moment. Okay. All right, so thanks for waiting. So, so the first thing that I ran was this GetJason command. All that does in the background is it uses Ajax, downloads a JSON file, and saves it as a variable called df. So you can look at that. Df, incidentally, is shorthand for data frame. It's really just a convention. I'm going to inspect the keys of this data frame. So this object.keys, you can also copy and paste it out of the slide. That's JavaScript. And object is the kind of the prototype for all the objects in JavaScript. And keys will let us look at the names of this data that we've downloaded. And let me explain actually what the data contains. It's a JSON file, and it contains a bunch of GitHub usernames. And each of these users has been ranked in terms of the number of projects they have and the number of stars they have. So we can actually do a few kind of interesting statistical tricks with this data set to, for example, find out who the most popular users are in this subset. So the very first thing I'm going to do is inspect the score of one of the users in this data frame. So I know there's a user on GitHub named Matt N. I actually forget the project, but I know that they're really kind of popular. And the data structure is a tree, and you can expand and dig into it. And the S value is the score. Just so you know, the score ranges from 1 to about 180. So this person is medium impactful on GitHub. Now I'm going to use the map function. I'm going to gather all the scores. So what I've pasted here, again, it's just easiest to copy and paste. But this general form, you can adapt to whatever problem you have. But the general form is that we're going to map using the keys, and the keys are the usernames, basically. And all we're going to do here is return the score for each user. So this is a very basic mapping function. It's basically looking something up in a database. That's kind of how you can think of things. All right, so let's run that. And we have some scores now. It's an array, basically what we would expect. And we can look at them, yeah, a bunch of integers, a lot of low values. So now I'm going to reduce these scores. And the way I'm going to reduce them is to do a summation, like I demonstrated before, but I'm also going to divide by the number of the number of items in this vector, and that's just going to give us an average, and that's a very useful statistical property. So when I look at the average, we see that the average score of all these GitHub users is 1.44. Now, the reason that could be handy is that was a small enough data set to easily crank through it on everyone's laptop. But the very nature of this calculation means that it doesn't have to be run on a single node. Each of these steps, and they're iterative, can be distributed across lots of different nodes at the same time. So I'm going to do one last thing here, which is actually to find the maximum score. And this is going to apply a function. The max math function will be applied to all the scores. And we see that whoever has the highest score is 48. The point here is actually that you all have kind of rudimentary data processing capabilities right now built into your web browsers. And you can do something like this, and it would be a legitimate analysis. I recommend migrating to a framework like Hadoop, but the point is you can get started immediately. So let's switch back. And I do have like a derivation here. We won't actually step through it, but this is like a mathematical expression for mean. We're summing over a bunch of values and we're dividing by n. And that is exactly equivalent to this MapReduce sort of breakdown. And like I say, the reason that's useful is because you can scale it up to a lot of different computers, and it's not important in the situation that I demonstrated because it's small enough data that you can do it on your laptop. But some of you might have problems that need more than one computer. And this is actually one way to get that done. So part of the point for this whole demonstration in the first place was to talk about SQL. So why don't we do some of that? This is the plan. We're going to use a built-in data set that comes with R. Then we're going to just start using SQL as a query language. We're not even going to use the database initially. And we're just going to sample, or we're going to select from this data set. Then we'll spit out that data as a CSV file. Load the CSV file into a SQL-like database, for those of you who've already got it. And then go back into R. And this time, we're going to select data out of the database instead of selecting it from within R. So let's see here. If you cloned the repo, and if I don't know if my pull request went through, but there's a, let's see. If you're in the SQL directory, you can make our notebook. I don't know if you can see that at the very bottom, but there's a little make file, and you can do make r-notebook, and it'll launch Jupyter with the R kernel. If you don't have the R kernel installed, this isn't going to work, and it's too much work. But just so you know, the lesson.md file has instructions for installing all these prereqs. So you can always consult that later. So, okay, like I say, the notebook has everything, so you don't even have to actually run this to benefit from knowing what the results would be. But I am going to run it just for your edification. So the data set that I've chosen is MT-CARS. That stands for Motor Trends Car Reports. They analyze cars, and they just recorded some data. So the very first thing I'm going to do is look at the number of rows and the number of columns. I just want to get a sense for the data before we actually do anything with it. And if I look at the first couple of rows, this is what we've got. The one column that I'm going to mess around with a lot is the cylinders. How many cylinders does the engine have? But it has other information like the weight and the name of the car and stuff like that. And look at the summary for all the variables and yada yada. So okay, I think I kind of get what data we're looking at. Now I'm going to demonstrate the SQL DF library. It has a couple of prerequisites. the RSQLite prereq is, we're going to come back to that one. So introducing some SQL. This is the first SQL of the whole tutorial. So what it says here is select star from empty cars where cylinder equals 6. Okay, and it's wrapped inside an SQL df call. So what this means is take this SQL and apply it to a data frame. That's how you parse the name SQL df. It's like it's an SQL and then apply it to a data frame. So what this SQL actually means is select everything from the data set that we're talking about, empty cars, but then filter and only return the rows that are 6-cylinder cars. So you run that, and that's what you get. There are 7 here, whereas originally there were, I think, 32 cars. So this creates a subset. Subsetting is extremely useful for a lot of stuff that you might be doing. So I do all this social research, and so I'm subsetting on different demographic variables all the time. So this is incredibly useful. And like I say, we can count up the number of rows that are returned from this. And in fact, it is filtering most of the results, except for the ones that have the 6-cylinder engine. Now, it's possible to get the same result in a different way, because SQL is actually a pretty powerful language. And one of the things that it can do is count instances of things, because that's something that you do a lot. And so this expression, select the count of star. Okay, the difference between representing it where the count is inside the quotation marks versus where I'm using R to count the number of rows is where is the calculation taking place. If you do it with the counting inside the query, then the counting occurs in the database server. If you do it with the counting inside R, then the counting occurs on your laptop, wherever that might be. It's possible that your database server is vastly more powerful than your laptop. So once again, there may be a major difference in where you choose to do certain calculations. And SQL permits you to move a lot of the calculations onto the potentially much more powerful database server. So what I'm going to do next is save this data set just so we can get to it from a different program. Now this is just R. There's nothing really special there, but if you you may just have a use for exporting data as CSV with some regularity. So feel free to study that. So what I'm going to do now is show you the contents of an SQL file. And this SQL file is going to create a table suitable for importing the data that we just exported. So let's see here. The file is called empty cars init, and okay. It is in the GitHub repo, but what you see here is a create table statement, and you have to specify the names of every column that will appear in your table. And so this is why I say that the schema is kind of fixed in cement. It's really inflexible to add or drop a column because you've got to use special SQL commands to specifically create each and every column. But I have done that specifically for the car data. And the rest of this file just simply sets SQLite to use the CSV mode and then imports the file. So I'm going to run that. Called make, I think empty cars init. Yeah, so there's a make file inside the lesson, and the empty cars init make item will import the data for us. So okay, it exists. I'm going to, and we're going to use R and query directly out of that database. It's going to be the same data, but it's coming from a different place now. So this uses the R SQLite library. And we're going to establish a connection to the database process. And now I'm going to list all of the tables in this database. And there's only one table. It's my results table. That's what I call the motor trends data. I said these are car results. But in practice, you're probably going to have lots of tables in whatever database you have. So you look at your tables, and it's a potentially constantly changing entity. So let me list the fields in that table. And not surprisingly, they are the names of the columns that I wanted. So at long last, I'm going to actually send real SQL to a real SQL database. It is the exact same query, except I'm querying for 8-cylinder engines this time. That's the only difference. But and the other difference, of course, is that now the query goes out to the database server. This is not simply R using a data frame. So I run it, and lo and behold, we get however many lines this is. So okay, that data came from a database.
Have you ever used dplyr?
I have, actually.
Because dplyr can convert its syntax into SQL commands.
Sweet, actually. I mean, that totally makes sense.
So it does, like, if you include it all in a pipe, then it'll go through the pipe, and at the very last end of the pipe, then it converts into SQL commands, and then it runs it through the database, and then you get the results.
Okay, so yeah, I mean
so
that
it keeps our code while still maintaining power.
exactly. So the interesting thing there, well, or no, there are many interesting things there, but one of them is the idea of pipelining, and does the complexity happen at the beginning or at the end? That's a pretty deep. So potentially you can go like very deep with these different database servers and look at query planning. So one of the commands that more powerful database servers support is called explain. And you can explain queries, or you can analyze queries. And potentially, by looking at the pipeline, you may find that there are certain operations that you should actually do, like at the very last second. I think Haley Wickham is amazing. So I haven't used dplyr with SQL, but probably everything that I've demonstrated so far would work just the same, actually. So for the Python demo, this is short and sweet. There's another notebook. I will load that in a second. But we're going to use the exact same database that we created, so it still has the motor trends data inside. We're going to send a query, this time using Python. And then we're just going to parse and print the result. I also will demonstrate using pandas briefly. So just a second. I also made a make command for this. So if you make Python notebook, it'll launch Jupyter. Once again, like I say, the results are saved, so you don't even need to run this to be able to see what's happening. So the very first thing that we do is we're going to use the SQLite 3 library that comes with Python, Python 2 and 3, and connect to the file that was created by SQLite that stores our MT cars data. And you've got to create a connection object. In this case, it's just called C by convention. And that maintains, that object is what you use to refer back to your your connection to the database server. So we're just going to get right into it. Let's just send a select query. I am demonstrating a little bit of the next level of sophistication here, which is using a variable called cylinders to perform a variable interpolation. So now we can just say any number of cylinders. This also is demonstrating how SQL injection exploits occur, because if it's not obvious, this is like a huge security problem. And that's part of why SQL can be kind of dangerous if you're not, if you're going to do it in the wild on the internet. So I'll briefly say the problem with this is that if somebody sets another value for cylinders apart from 4, you could say my value for cylinders is some valid SQL that would drop all the other tables in the database. And if the people have not coded to prevent that, then it's actually possible for people to just type whatever variable name they want and wreak havoc on the server. Good libraries for using Python and using any language to connect to a database server, good libraries will prevent that kind of SQL injection. So okay, let me actually run these. Okay, I have sent a query off to the database, and now I'm going to do a few things. I'm going to fetch the results. I'm going to attach variable names to those results, and then I'm just going to print out a subset of the results. I'm going to print out the names of the cars and the number of mileage per gallon. And that's what it looks like. And the very last thing I have to show for Python is an example of getting that same information into pandas in case you'd rather do your analysis with Python and pandas instead of R. So that works, and that is a basic example that you can build off of. So the
to scale.
Oh, you mean instead of using like the pandas facilities for merging like two pandas frames? Right. Yeah. So I mean, again, okay, what happens on pandas happens in memory. And like if you have a lot of RAM, then maybe that's okay. But if you have more data than can reasonably ever fit into RAM, there may be some operations that the merge can only really be accomplished through some disk-mediated process, and that is possible. That's the kind of task that a database engine will be up to. Pandas might be able to fake it with kind of like a virtual memory sort of swap disk kind of thing, but you're at the mercy of the operating system. With a database engine, you have control, like total control over the performance characteristics. So I would say that that one of the reasons might be the scale of your data, but the other reason might be that it's just harder to think about it in terms of the pandas expression that would merge the data. So I don't have any super complicated queries that I'm going to demonstrate, but so all SQL can be represented as a kind of a more basic form of mathematics called like a relational calculus. And sometimes there are problems that are easier to think about using certain frameworks instead of others. Like this is a good relational calculus problem, this is a good graph theory problem. So I could imagine actually that you might just have an easier time thinking about a certain type of query as SQL as opposed to pandas. Don't have a great example off the top of my head, but it changes the way you approach it. And we could get philosophical about that, but maybe another time. So anyway, all All right, let's see. I think I've got just a little bit more to show regarding some SQL inside SQLite. And this, I'm not actually going to run everything. I'm going to point you in the direction of the data file, and I'll pull it up and we'll look at it. But I'm not actually going to like literally run all the commands. But so you know, there is an SQL file designed for SQLite inside the lesson plan. And each one of these points is more or less a comment. And after that comment is an example of using that command. So let me quickly go to that. So it's study group lessons. This lesson is called SQL, and the file is examples.sql. The basic idea is I showed you how to import data. Well, here I have a quick example of exporting data from SQLite. I do have a minimal example of creating a database table and then dropping that table. And like I say, imagine we're in SQLite right now. We're actually typing commands directly to the database engine. So each of these commands here is the same kind of SQL that I already showed you in R and in Python, but now we're just sending it unmediated. So examples of selecting, counting, renaming things on the fly, inserting new values into the database, and then using slightly more complicated queries, like maybe finding all the cars with engines greater than 5 cylinders. So that, and all of these things, appears in the lessons in the SQL directory. I will also point out, this is where the R and Python notebooks are, as well as the make file. And I think the last thing that I want to say, is actually just that the URL for the presentation itself is iandennismiller.github.io/databases-SQL. So why don't we leave it there? Thanks.